Okay, welcome back to the second part of our session 4. The next team and our speaker, Steve Longmore, has the small task of presenting to us the question of the formation and early evolution of young massive clusters. Once again, we'll have questions at the microphones afterwards, and I'd like to hear a little bit more from the upper gallery here. The next session, please.
Yep, thank you. Yep, test. Okay, well, good afternoon, everyone. So I'm going to show some of the results from our chapter reviewing the formation and early evolution of young massive clusters. But before I do that, I want to do a couple of things. First of all, to thank the rest of the team here. It's been really fun working on this. You'll notice that quite a few of them are already here. So Diederik, John, Leonardo, Andrea, Eli, and Jim are here. And that's great for me, because if I get any awkward questions, I'll just defer to them. It makes me happy. Unfortunately, some people couldn't be here. Nate, Jill, and Joe are not here. And that's even better for me, because if I make any horrendous mistakes, I'll blame them. Just joking. Okay, yeah, so I'm going to be talking about the formation and early evolution of young massive clusters. But before I get onto that, I really want to try and just spend a few minutes saying, why should we care? Okay, well, as we go through this week, I think it's clear over the last few decades, really building up the basic picture of isolated low-mass star formation is quite well understood, and it's been underpinned by many observations, very detailed work studying these nearby regions. So my question is, how typical is the star formation in Perseus or even Orion compared to the environment of most stars across cosmological timescales? So what I'd hopefully like to convince you by the end of the talk, this is our schedule here, and I'd like to convince you by the end of the talk that what I'm going to be discussing today, young massive clusters, in terms of the larger scale global processes and things that we, in the gas, that we've been hearing about earlier in the week, and the more detailed physics of how you form the stars and planets, that young massive clusters are a bridge linking between these two regimes, and we can learn a lot of key details using young massive clusters. Okay, so let's ask the question, how typical are nearby star-forming regions? Well, let's start with 3 facts. Fact number 1, 50% of star formation in the Milky Way takes place in the 24 most massive GMCs. Fact number 2, the peak of star formation rate density happened redshift 2 to 3. And I think it's fair to say that most stars in the Milky Way are older than a few gigayears. So what does this mean? Well, even the Milky Way at the present day, these nearby star-forming regions are not typical. Your typical star in the galaxy is not forming in something like Perseus. The average gas properties in redshift 2 to 3 were substantially different. So if you have stars that are formed at this epoch, then does it actually make sense to compare something that formed a long time ago with, if you're looking for planets around nearby stars in Kepler or something, to the disks in nearby regions? So the point here is that, well, maybe these nearby regions aren't representative of star and planet formation across cosmological timescales. So the fundamental underlying question here that we should be trying to probe, how universal is this process of converting gas into stars and planets? And to what extent can we take what we know in the local universe and take it out to the far reaches of the universe? And so the thing that we should be asking is, does the physics of star formation care about its environment? If the answer is no, then all we need to do is look at these nearby regions, study them in as much detail, throw all the telescope time that we can at them, and that will tell us everything we need to know. But if the answer is yes, star formation does care about environment, it's crucial to understand how and why it might change over these various environments. Okay, so here's the outline for my talk. I will start a bit about what are YMCs and why are they so important before talking about the theory and observations. So what are they? Well, if you were to ask someone what a cluster is, you go back to your undergraduate days if you can remember that far back. And there's 2 types of clusters. There's open clusters and globular clusters. This is a radius mass plane. And open clusters are much smaller. They're young, they form recently. And globular clusters are old, they formed at early epochs of the universe, much more massive and dense. So these young massive clusters fit in between. They are as massive and dense as globular clusters, but they're forming in the present-day universe. So the question is, are these YMCs, the young massive clusters, the missing link between open clusters and globular clusters? Or are they local universe analogs of extragalactic superstar clusters? So, what are they? That's a kind of bit of a vague definition. It always helps to look at something to know what you're talking about. This is a beautiful image of Carina from Thomas Preibisch, his group, in the near infrared. And this is Trumpler 14. So this is a stellar cluster with 10 to the 4 solar masses in radius of less than half a parsec, 2 megayears old. The dynamical time, so the time it takes a star to cross from one side to the other, is only 0.12 megayears. So from that, using this pi, this ratio of these two numbers, we can tell that it's gravitationally bound. So this is a bona fide YMC. But hang on a minute. It's sitting in a sea of other stars. So what's the deal with that? No, this is not a YMC. This is a YMC's surrounding association. And through the talk, I want you to take one thing very much in mind. We are not talking about YMCAs, young massive clustering associations. We're talking about YMCs, the very dense components. Okay, so why are they such good laboratories for the sort of thing that we're doing? Well, let's ask the question. I'm a star, and I'm born in a superstar cluster, or I'm a star and I'm born in isolation. How's my life different? So whether you're born in here or here, I think you'd agree you're going to have a very different life in terms of the stellar density, in terms of the number and the proximity of the high-mass stars, the dynamic interactions, protostellar feedback. You're going to have a much tougher life in the middle of a superstar cluster. So if you want to have an end-to-end understanding of the star and planet formation process, you better be able to explain what's happening in both these regimes. Okay, so kind of to summarize, YMCs, they're ideal probes because they're extreme. So if you understand star formation, these are the things that you want to be studying. In terms of the IMF, we had a really good talk yesterday about the IMF, and I would argue that YMCs are the place to look if you want to study how you assemble IMF, because you've got a large number of stars at the same age, and they remain bound for a long time, so you can see them for a long time. They're also, statistically speaking, the best place to find the next beast. So where's the next 100 or 200 solar mass star going to be born? Statistically speaking, it's going to be in the progenitor of one of these systems. And as I said before, this is a bridge between open and globular clusters. Okay, so theory. What do we know? It's difficult. And that's because there are many processes that are involved in getting a large gas cloud into a large number of stars. You first of all, of course, you have to take account of the fact that gas is getting converted into stars, but then the stars kick back. There's some feedback. You have to worry about star-star interactions once you've got the cluster there. And then you have to care about the external environment. Once you've formed the cluster, does the environment affect how long it lives? Now the problem, if you're a theorist or a simulator, is you've got to have a pretty big toolbox to address this question. You've not only got to be able to deal with the gas, you've got to be able to deal with the stellar interactions, feedback, and in terms of the dynamic range that you have to probe, in terms of mass, size, and time, this is much larger than can currently be simulated. So unfortunately, this is difficult to do, and I don't know of any simulations that have really probed all these things in detail. So the theorists are smart, and they can tell us some things. Even without having run these simulations, they can tell us some things about it. And the take-home point here is that density is key. Density is really the thing that determines whether you get something that's bound or not. And the reason why, it's sort of quite conceptually simple to understand. So imagine I'm a star forming in a region of very high density. Then most of that gas is going to go into stars before the protostellar feedback. So once the feedback switches on and you get rid of the gas, you don't care because the potential is dominated by stars. And the conversely thing happens if you're born in a low-density environment. Now, that's all well and good, hooray, but clouds are not spheres. We've seen beautiful images by John yesterday from the High Gal, and also from Philippe, that things are filamentary, they're complicated, they're multi-scale. So what does that mean? You have to understand the mass as a function of size scale. And in particular, where does this gas exhaustion occur? Is there a critical density at which this happens? Okay, so in terms of the theory, what we really need to do is understand what the distribution of mass as a function of size scale is at the very earliest stages, before you formed any stars. And that really is what we need to feed as observers into the theoretical side of things. So what we need to do as observers is focus on this earliest stage. Okay, so that's what I'm going to spend pretty much the rest of the talk focused on. So we can do one thing. We can take a telescope and point at a random position in the sky at a random wavelength and see what we find, or we can think a bit about what we might expect to see. So what might we expect to see? We know the stellar clusters have these properties. This is the radius and mass, the same thing I showed before. What must they look like? Well, we can say for sure you better have enough mass. If you don't have whatever stellar mass divided by some star formation efficiency, forget it, go home. There's not enough raw material. And it better be sufficiently dense. You can take a whole bunch of mass and put it on 10 megaparsecs. It's never going to form a stellar cluster. So you can be, that's a sort of very hand wave, you can be a bit more quantitative and say, well, after you start forming stars, it has to be bound, gravitationally bound. So if you want, let's take ionization, for example. This is work by Eli Bressert. You have to say the density is sufficient that the escape speed in the cloud is greater than the sound speed in ionized gas. So effectively what happens then is the ionization is bottled up and it can't blow out the gas. So you can play games like this to get what sort of parameter space you're interested in. But can we quantify exactly how dense? Remember, this is the key thing we've got to be focusing on. Well, yeah, again, we can do it in a sort of hand-wavy fashion by considering some different potential formation scenarios. So let's take a YMC of a given mass and radius. And let's ask the question, where did the gas that eventually ended up in that YMC start from? So another sort of subtle underlying question here is there a unique way to do this? There may be multiple ways. So bear that in the back of your mind. I'll come back to that at the end of the talk. So the two sort of no-brainer things that you can think of, maybe you have collapse of an individual cloud, or maybe there's converging flows. We've heard both these things mentioned this week. Cloud-cloud collisions. Okay. So volume density is the key. What does this mean for the initial volume density of our gas clouds? Well, I'm just showing here, this is lines of constant volume density, and this is a factor of 125 difference in the average volume density. And you can see that potentially these things can span a very large initial range in the volume density. And if density is so important, it's crucial we understand what this potential range is. And just to highlight, the most extreme version of this is where you get all your mass in a particular volume, and kablooey, it forms stars. So the gas is forming at the same, stars form at the same density as the gas. Okay, so this is, again, interesting. We can get slightly farther in this hand-wavy approach by considering different potential scenarios. So now here we've got our star cluster of a given radius, and we're going to consider two potential mechanisms. So on the first, we have that the gas cloud you start off with, this R init, the initial radius, is the same as the final stellar radius. And you just somehow magically get your cloud there, kablooey, stars. Done. Another potential situation is where the initial radius is significantly larger than the final radius, and somehow this proceeds to shrink to form a stellar cluster. So what are the implications of this? Well, obviously, this gas is initially at much higher density, but a crucial thing, you need to have convergence of the gas flow. And what mechanism that is, there's several potential mechanisms to do that. So just for the remainder of the talk, I'm going to refer back to these in two different ways. I'm going to call this in situ formation, and this one here as a conveyor belt formation. This is deliberately to hide any physics behind what might be doing the conveying. So I'm dodging a bullet before I get hit. Okay, so observational predictions, this is pretty easy. So you can ask the question, are there any gas clouds with M gas is M star over some efficiency in R gas equals R star and no star formation? And if the answer is yes, then we're sitting in this in situ regime. If the answer is no, then we're in conveyor belt type mode. And this is the most simplistic thing. There's another criteria that you better be seeing some gas kinematics that are showing signs of infall in here. So just to reiterate that if things like feedback are important in a volumetric way, then this comes in as a cube here. So it's really crucial to understand which of these operates and when, or none at all. Both. So we're trying to get at. So the key diagnostic is finding the mass and radius of the progenitors before there's any star formation, and that's really important, because by the time you're down in this stage here, it's all over. Okay, so observing diagnostics, well, we've known for a long time that if you want to observe very young, early star-forming regions, you need this cold, dense gas, so things like the millimeter continuum or high critical density lines in the millimeter. So we already know what we should be looking with. And so the current facilities, in this wavelength regime, you can't go past ALMA, of course. And if you do some very sort of simple back-of-the-envelope calculations, you come to the conclusion that it's going to be possible to compare the progenitor clouds of YMCs out to large distances at tens of megaparsecs with ALMA. But very, very, very important point. The only place in the universe for the foreseeable future where we're going to be able to resolve individual sites of star and planet formation, so I'm not talking about the global properties, but the individual sites, is in our own Milky Way. And that's important. That makes this is a unique template. It's the only place we're going to be able to do this. So this provides a really strong motivation to building up a complete YMC progenitor sample in our galaxy. Okay, and unfortunately, this is actually really quite new. We've only recently been able to have large enough surveys that we can look across the whole galaxy in sub-millimeter wavelengths at high enough resolution that we can begin to pick these out. So I'm just going to sort of quickly go through it and try and show you the kind of excitement and what things will be coming online soon. We don't have any definitive answers yet, but this is something that's going to be in the next few years, something to keep an eye on. Okay, so status as of January 2012. This was a paper we published where we sort of got a hodgepodge of the data that was out there and had a look. And you can see that, so these are now the gas clouds overlaid, and most of them in this mass radius plane look like they're going to form open clusters. Kind of a bit boring, really. We did find one cloud that got us interested, and so kind of what sparked certainly my interest off in this whole schmozzle. But that's old hat now. Ignore that. That's already a year old. So what's happened since 2012? And that's where I'm going to spend the next the rest of the talk. So there's 3 regions now where we have what are complete or nearly complete samples, and these are the inner 200 parsecs of our galaxy, the first galactic quadrant, and the 4th quadrant outer galaxy. I'm just going to spend some time explaining what we know based on these data sets. So this is the inner 200 parsecs of our galaxy, so you recognize that from John's talk. This is inner 250 in here, and this is at Spitzer wavelengths. If we go to slightly longer wavelengths, we see that some of these clouds are still showing up in absorption at 70 microns. These are dense. These are huge column densities here. Some of your famous SAGB2, SAGC, some of the clusters in the center of our galaxy there. If we go to even longer wavelengths, now of course this dust that's blocking the light comes out in emission. So these things are whoppingly bright at 250 microns. So just as a reminder from what John was saying yesterday, if you model the kinematics of this gas, this kind of infinity symbol, it's supposed to be overlaid-ish. That's what the way you model it looks like this. Here's some of the clouds. This black solid line is supposed to be the front, and this is the back of the cloud. So if you model that as this twisted ring that's orbiting in this way around the galactic center, 2 oscillations every orbit, and at 80 kilometers a second. This is Sergio Molinari's paper. So if you, instead of looking edge-on, we could magically turn our galaxy to be face-on. This is what we'd expect to see. So again, the black solid lines here are that rotating here, and Earth's down this way, so we're looking up like this. Okay, so it turns out we have a column density map, because we know the distance to this, and we have some idea of the kinematics, so we can tell what's at the galactic center. And based on that, we can estimate, we can ask the question, are there any YMC progenitor clouds? And this is a technique that we use to do that. So we have a column density map. And one thing you can say for sure on a column density map, once you've got the distance, is that if you have an area, then you've got an enclosed mass. Very simple. So what you can do is you can take an aperture of a given size and say, okay, tell me what is the mass in that aperture size. You do that for 1 pixel, you can repeat that for all the pixels across the map. And you can do that for many different aperture sizes. And this way you build up an idea of how much enclosed mass there is as a function of position across your image. And this is what you get if you do that. So this is just done with 2 different apertures. So the color scale is shown here. This is the mass in solar masses enclosed, 2 different radii. So this is for a radius of 1 parsec, and this is a radius of 3 parsecs. And the reason why we chose those is because that's related to the tidal radius, because we're very close to the galactic center. So this gives you some idea of what its size scale is much larger than that. The gas starts getting shredded apart. Okay, and the black contours show areas which pass this threshold criteria. And importantly, the gas, we can also go in and look, because we've got molecular line information, we can tell these are coherent features with velocity dispersions that are consistent with being at the galactic center. So we're pretty sure we know what these things are. So that's what's shown here. And we have some idea of what kind of star formation is going on within them. So there's 2 that are going gangbusters. So this is SAGB2 and SAGC. There's 4 with almost no star formation. And there's a couple that are potentially interacting with SAG-A star. So I'm not going to talk about those because we don't know exactly what the fate of those is. Okay, so that's what we know about the inner 200 parsecs, or about the first quadrant. This is work by Adam Ginsberg and collaborators, where they used the BGPS in the first quadrant, and with a flux-limited search, were complete for clouds of 10 to the 4 solar masses or larger in radii of 2.5 parsecs or less. And what they found was that there were 18 clouds that passed this criterion, 3 of which were more massive than 3 times 10 to the 4. But the really important thing, and the big difference between this and the center of our galaxy that I'm going to come back to later, is all of these, every single one, has prodigious star formation activity. That's going to be important. So then finding that the fourth quadrant of and the outer galaxy, this is work that had been done by the AtlasCal team and the collaboration. They've been working incredibly hard on their data and getting some really interesting science coming out. So this is a really nice paper by James Urquhart, where he has used AtlasCal and combined that with the methanol multibeam survey and picked out regions, and again this is now the radius mass plane, and this is the regime where you expect to find these YMC precursors. And his paper shows that there's 6 that passes criteria, and including one thing I've not chatted to him about yet, but there's a beast up there with 3 times 10 to the 5 solar masses and a radius of a few parsecs. Very interesting. This is work, so Yanette Contreras is working on, so she is taking the AtlasCal data, but instead of combining with the methanol multibeam survey, she's combining it with MALT 90. So this is MALT 90 is a molecular line survey with the MOPPER radio telescope that's PI'd by Jim Jackson, and Jill Rathborne and Jonathan Foster are doing great work putting this together. And they also find a bunch of candidates. So this is potentially very interesting. I'd also like to point you to a poster, 1B040 by Zarota, where entitled "The Most Massive Gas Clumps in the Milky Way." Now, can you imagine why that caught my attention? So I suggest you go and look at that. And also, yeah, just as a general quiz, if I missed anything, any posters, please come and see me. I'd like to include it in the review. Okay, so kind of to summarize that, these are really potentially very interesting results, but unfortunately we don't know the evolutionary stage of these things, so it makes the next comparison I'm going to do difficult. So this is something interesting for the future. Okay, but what we do know the star formation activity within these clouds in the first inner 200 parsecs in the first quadrant. So now we've got to take that and put our money where our mouth is and try and say something about the way you form YMCs. Okay, so now we're going to compare these 2 regimes. I've got 3 rows here. On the top is clouds of mass greater than 3 times 10 to the 4 solar masses, radii less than 3 parsecs, little or no star formation. This next row is exactly the same mass and radius, but now with prodigious star formation. And finally, the YMCs themselves. In this case, we've chosen ones that are less than 2 megayears for reasons I'll explain in a minute. Okay, so we've got 2 columns, 200 parsecs in first quadrant. So what do we see? These are the numbers. It's like football scores or something. So, okay, but before we go and try and do any physics with this, is this a fair comparison to make? And I would argue yes, but only if the present-day gas clouds that you're seeing will produce statistically the same stellar population that you see at the present day. That's the first criterion. And the second one is that cluster disruption is not important, because if clusters get disrupted at different rates and you try and compare things down here, you might get in a bit of trouble. So we checked to make sure. Now, both these regions, we know that the central molecular zone of our galaxy has 10% of the molecular gas, and the first quadrant makes up 30%. The region reviewed by Ginsburg makes up 30% of the total galactic area. So we're pretty sure that in terms of sampling and statistics that we should be doing a pretty good job. So criterion 1 seems satisfied. In terms of cluster disruption, this is something we have to be extremely careful about, because the galactic center is not a nice place to be a star cluster. You don't live very long, a few megayears. So we were very careful, and we chose to compare to clusters of 2 megayears or less, so that they should be comparing apples and apples. Okay, so in which case, when we can take these numbers at face value, what can we learn? Well, we have the same number of YMCs in these 2 regions. We have similar number of prodigiously YMC clouds, prodigiously forming stars. But we have vastly different number of clouds with no star formation. There's 4 in the inner 200 parsecs and none in the first quadrant. So I would argue this is telling us something important about the way you assemble your mass into YMC. So what's going on? Well, let's refer back to the predictions we had for those various different mechanisms. So this is that same slide I showed earlier. I remember the key diagnostic was the progenitors with no signs of star formation. And, well, these numbers are telling us that the galactic center clouds seem to be this kind of in situ mode, and in the disk is this conveyor belt formation. OK, so what are the implications of this? Well, I mean, straight off the bat, if this holds, then it's telling us that there's different ways that YMCs can assemble their mass. There's not a unique way. If you see a stellar cluster of a given mass and radius, you cannot say, I know how that thing formed. You have to know something about the star formation history of that object. And potentially depends systematically on the environment. OK, let's take a step back. This is all interesting. We've counted a few objects, well done. But it doesn't make sense in the physics. We've studied some of these objects in a lot of detail. So does it make sense with this picture putting forward? So let's look at the two regimes. So first of all, the first quadrant, this is shown here. This is a view, face-on view of our galaxy from the review by Portuguese Svartstal. And the region looked at by Adam is shown here. And there are two very well-studied regions, the YMC precursors in this area, so W43 and W49. And both of these are recent papers. W49 has been studied by Roberto Galvan Madrid. And W43 has been studied in a lot of detail by Frederick Mott's group, including Quang Nguyen Leong. And both of these show signs of large-scale gravitational collapse feeding these YMCs. In particular, W49 has a sort of central hub that's getting fed by filaments from 60 parsec scales. So this is just two regions. There are many other regions in the galaxy which qualitatively show similar signs of sort of large, these conveyor belt type things. So these are some studies within our galaxy. There's even a study by Professor Fukui's group looking at you look at a YMC and you see what's left after that's formed. And they say there's evidence that they can still see the remnants of the clouds that have collided together. So and that's two out of the 4 objects that have been studied. So there's a 100% success rate in finding these. There's extragalactic studies. And I want to really highlight 2 people who've been sort of working on this for a long time. Eric Quito and Pamela Klassen have done a lot of work on the bright H2 regions, looking at infall signatures. So their work, there's 2 I need to put on here. Again, at this meeting, I'd like to highlight a couple of posters, one by Cara Battersby, one by Johnny Henshaw, one by Helen Kirk, looking at sort of large-scale mass flows. So there seems to be evidence, at least, I mean, this might not describe everything, but it certainly doesn't seem a totally wacky idea. And again, please let me know if I missed anything else. OK, well, certainly this conveyor belt appears to be consistent. I mean, this definitely is not proof. I'm not saying that we've solved anything, but this is certainly an interesting avenue for following up. So what about inner 200 parsecs? Well, now let's return to this picture that we had. So this is the enclosed mass as a function of radius. And it turns out that if you look in detail, there's a couple of interesting things to notice. First of all, the observant among you will have already noticed that the dense gas is not uniformly distributed. It's found in a particular location. So is this an asymmetry in the mass distribution? What's going on here? Well, we can attempt to answer that question. So what we do is we divide this region into 4 equal areas that bisect the middle. We avoid the tangent point because we don't know that's things piling up along line of sight. And we can simply sum up the mass in each of these 4 boxes. And if you do that, you find that the mass agrees to within a factor of 2. That tells you that the mass is constant on the ring, but the density is changing. OK, so what's causing this increase in the density? Well, then we come to our intriguing fact number 2. The geometric center of this ring, the natural expectation would be the center of our galaxy, Sagittarius A star. Wrong. Turns out that's not the case. This is where you might expect the center of our galaxy to be, Sag A star, but in fact, it's here. It's closer to the front side of the ring than the far side of the ring. OK, so you put these 2 things together, and as a naive Scotsman, you say, well, is the gas being affected by this close passage? Well, let's see if it makes sense with the rest of the data. So we have, here's Sag A star. Remember, the gas is going in this sense here. So the gas, all these dense gas clouds are up here. All the more diffuse stuff, remember, this is still dense. This is still 10 to the 4 per cubic centimeter, but it's just less dense, is on this far side of the ring. There's evidence that these 2 clouds here, called the 20 and 50 kilometers a second cloud, are interacting with Sag A star. So when you look in detail at this particular object here, this funny banana, there's not very much sign for star formation there at all. So there have been several really nice recent papers looking at this. And there's also evidence for tidal stretching that I'll come back to in a minute. And then there's also evidence that there might be more star formation activity farther downstream. So certainly, in a kind of hand-wavy sense, this seems vaguely plausible. But of course, we don't like hand-wavy, so we want to test that. But just before we do that, we need some idea of what the scenario might be and some predictions for it. OK, so hypothetical scenario. So you have gas that for some reason is not forming stars. It's on the backside of the ring. It's just floating around doing its own business. And then a very inconvenient thing happens as it starts to fall down the bottom of the galactic gravitational potential. I can't imagine that's terribly pleasant. So what happens is that the gas comes down and it gets squashed. It gets compressed by the gravitational potential. And energy is injected into the gas. You know, if you were a star cluster, you wouldn't care. You'd just go past the bottom of the potential and re-expand. But gas is dissipational, so on a crossing time, that energy gets dissipated. So basically what happens is you have shocks, and after pericenter passage, the gas is very dense, but it can begin to collapse and form stars. So our predictions, the strongest shocks in the gas should occur near the pericenter passage. The cloud should be, just because of tidal interaction, should be stretched along the orbit and squeezed perpendicular to the orbit. So that's this guy here. This is the orbit. And this one, certainly circumstantial, but it certainly is elongated along it, and it's the most compressed bit perpendicular. And we predict that this is evolution of star formation. So we want to test those predictions. So we've got some kind simulators to see, is this even vaguely sensible, or am I making a fool of myself? And there's 3 different groups that are willing to test if I'm crazy. It's not a surprise, really. So this is a group led by Diedrich and Jim. Will Lucas and Ian Bonnell, a different group, and Paul and Simon are running thermodynamic models. And so doing some comparisons, this is early stages, but certainly I think it's fair to say that the initial comparisons have been very promising, and the scenarios at least passed the idiot test. So this is, potentially an exciting, I'm in danger of getting too excited here, so I'm going to try and tone it down. But this is potentially really exciting because normally when we try and investigate the IMF, we have to do it in a statistical sense. We get a bunch of regions of the same mass and radius, and we, similar properties. Then we look at things that are hopefully similar at a slightly later stage, and then we look at some clusters. We have to do it in a statistical sense. If this turns out to be true, we can follow the IMF, we can follow the assembly of stellar mass as a function of absolute time. We know the gas orbits the galactic center in some way. We know when it passed Sagittarius star because we know its rotation velocity. So we can watch these clouds that are farther downstream and see how they progress to form stars. And I'm very excited about this. So, and I'll show you some ALMA data, our first steps attempting to do that. So, in summary, our current data suggests there may be different ways that a YMC of a given mass and radius can accumulate its mass. The one thing that definitely sticks out here is the galactic center is extreme. The thing that I'm personally very excited about is we might be able to follow the assembly of stellar mass as a function of absolute time. And I'm going to leave you as a little teaser here. Please come and talk to me about that. But Diedrich and I have a paper recently where we've compared the regions from everything from the nearby universe up to things at high redshifts and compared in a scale-free way what the properties are. And we argue that the Milky Way is a fantastic reservoir that covers a lot of these range in the star-forming conditions. So I would argue that you can. What we learn here, we can go to the cosmologist and say, hey, listen, we can tell you something. OK, so in terms of future work, we all obviously want to know, is our galaxy atypical? Is it weird? Can we find evidence for this in other environments? And the elephant now in the room is, where are the progenitors of the YMCs? We see lots of YMCs in the disk of our galaxy, but we still haven't found a progenitor that's not yet forming stars. So that would be big. If anyone, that'd be a really exciting result if someone can find that. So one thing I'm particularly interested in, remember that the Milky Way is the only place for the foreseeable future where we'll be able to resolve individual stars in an environment like this. So that means that the center of our Milky Way is the most extreme place that we'll be able to resolve individual stars forming. And that makes it very important. So comparing that with things in the outer galaxy, this, I think, is potentially exciting. Yes, I won't bore you with that again. So now I'd like to, how long have I got, Ralph? A few minutes, cool. All right, so I'm going to show you some ALMA cycle 0 data. I've been waiting all talk to show you this, because this is just amazing. OK, so this is the same picture I've showed you again, and we were lucky enough to get ALMA cycle 0 observations of this cloud. managed to pick up various names, G0.253, M0.25, the lima bean, the brick. And so this is just showing you on there. It's this thing here, but this is in galactic coordinates, and it was observed in equatorial, so there's going to be a slight shift, but it's the same object. OK, before I show you this, two important things. One, Jill Rathborn, she's the PI of the project. She's been slaving away for 6 months on this, and you'll see why. This is the data is so complicated, it's very difficult to analyze, and she's doing a fantastic job of doing that. But I also want to say a huge thank you to Crystal, who was the contact scientist and did a lot of the initial work doing all the quality assessing and stuff. And there's a whole army of people spread throughout the world who are doing this behind the scenes, not just for this data set. So a kind of general thank you to those. Anyway, so here is what our previous best image of this object looked like. This is a 450 micron scuba image of this cloud, the brick. So just to give you some idea of the size scales we're looking at here, this is like a few parsecs across this way, I think 4 or 5 parsecs or something. The mass, 10 to the 5 solar masses. It's a bit of a beast, very dense. Average volume density, 10 to the 4 or something. So this is what you see in the best. And remember, so we're trying to understand, what does the mass do as a function of spatial scale? That's key to try and understand. And at this resolution, you think, we can maybe do something here. There's a couple of blobs and whatnot. So when we look with ALMA, 3 millimeters, this is what we see. So we get a very different picture. Quite spectacular. And this thing here is not a fly on the wall. This is our resolution element. So that's continuum. That doesn't tell you that much. There's a whole lot more information here. We have 16 molecular lines, and each of them has kinematic information. So just to give you an idea, I'm not going to go into detail, but I want to impress upon you the complexity of this data set, number one, and number two, just ALMA is really changing things. As someone who's spent a long time looking at interferometric images with 6-element interferometers, I've got really good at counting blobs and doing stuff. It's difficult to do that with a data set like this. OK, so this is just showing some different transitions, all the very complex morphology. We worry about chemistry, excitation. I can show you some different molecules. Everything looks completely different. I'm just going to flick through just so you can get some idea. These are the integrated intensity maps. So 1, try and tell me where there's a core in this. And 2, tell me what these filaments are. Anyway, lots of questions. So there's some papers coming out soon. Keep your eyes peeled. To some other transitions. These ones are less optically thick. And of course, we have the kinematic information too. So this is HNCO, a molecule I hadn't really heard about before before we started observing this cloud. And now I'm showing you this is the velocity information here. So you see there's a big velocity gradient, but just look at how complex that velocity structure is. It's sheets and arcs, and there's a big... Okay, and this is SIO, which everyone knows you just see in small, isolated, compact things near where stars are forming, but not in the central molecular zone. So it takes a while. So these are big movies, big data sets, take a while to load. So this is SIO. So you can see it's not only the compact knots, but there's diffuse stuff. We see these arc-type filaments, long linear features. Don't get tired of looking at that. Wonderful. OK. So on that note, I will leave up my summary slide and future work. And with the plea that if I missed anything or you think there's some aspect that I've not included, please come and see me, and we'll try and do our best to put it in the review. So thanks for your attention.
Thank you for that provocative talk. So, sure, there's lots of questions. Let's get started.
Kara Battersby from the University of Colorado.
Hey, Kara.
Nice talk, Steve. Thank you very much. So my question is about the in situ star formation idea. So when you're above the Bressert criteria, it's highly gravitationally unstable. So you wouldn't expect these objects to be very long-lived. And so the fact that you see so many of them in the galactic center almost rather implies that they're not going to be forming stars because they should have collapsed very quickly.
Yep, so I completely agree with you in the disk, but there's a paper by Diedrich, it's on AstroPH, explaining why star formation is slow. It just turns out that there's a lot more energy in the gas. So if you look at the line width size relation, these things are a factor of 5 larger for given the line width. So there's a lot of energy in these clouds, but the thing is, there's energy in it at the moment, but turbulence has to dissipate. So the question is, what then happens once you dissipate that turbulence? So I completely agree with what you're saying if you're in the disk. I think the galactic center is weird.
And just one quick follow-up question.
Yeah.
So with the in situ situation, you say that the initial conditions would be like that, but obviously there's something that comes before that. I was wondering if you had any thoughts about what the previous state of that would be.
Yes, I have thoughts, but no answers. This is something that's going to be particularly interesting. So Henrik Beuter's Thor programs are looking at H1. I think that's going to be really interesting, looking at what these H1 envelopes are doing. That might tell us something about the kinematics of these gas. But the problem is, I say, we don't know where any of the initial conditions are for things in the disk. So finding one would be great, and then we could look at the environment.
Agreed, yeah. Okay, thanks.
Any questions from the gallery? I can't see Pharrell from here. Questions up there? Okay, very silent. Okay, down here, Hans.
People getting tired. I'm not. Steve, can you show us again the continuum image?
Of which? Sorry.
Of the brick.
Of the brick, yeah.
So.
It's going to take a while because I've got to.
Sort of as following the story a little bit here, I was wondering actually whether this picture with the density clumps and enhancements, of which you probably have an estimate, maybe they're 10 to the 6 particles per cubic centimeter, I don't know. But this cries out, since no stars have been formed, this cries out as being the initial condition for a star cluster formation. So you mentioned people calculations, plans. So is that what they're going to do? They take this as for their SPH codes or AMR codes and simulate what the final outcome will be?
Yep. So I can tell you. So what?
And what is the mass of the individual clumps there?
So these are surprisingly small. So there's a really nice paper by Jens Kaufmann, so looking with the SMA, and they show that the most massive thing in there is probably only a few hundred solar masses.
Well, but every one of these clumps is enough mass for a massive star.
Yes, but so this is the interesting thing is, if you've got something at 10 to the 5 solar masses, and we do think, to answer your first question, yes, we do think this is the initial conditions.
Yeah.
But wouldn't you expect to see something? If this thing's going to form, say, a few hundred solar mass star, and the most massive thing in there at the moment is only 100 solar masses, then it's difficult to form something directly.
Well, you can form the more massive stars later by collisions. You don't have to form them right now.
Okay, thank you, Chris.
Yes, that was a very stimulating talk. I wanted to ask a little bit more about the disk YMC progenitors, which you said are forming stars at a prodigious rate.
Yes.
So my question is, what fraction of the YMC has already been formed? If you look at the star formation that's underway now and say it stopped, are you saying by the adjective prodigious, well, you already would have formed a third of the YMC anyway?
That's a good question. So I can give you numbers in terms of Q. So these are the W regions, showing you W49, W43. So these things have Qs of 10 to the 51 or something like that. Luminosities of 10 to the 6. Oh. So that tells you that you've got to have some serious amount of star formation there. What I can't tell you is, I guess, because when you take luminosity, you're not sure how much of that is accretion versus, and do we know what a pre-main sequence massive star luminosity is? So there's many things. So I can certainly come up with a number for you. I don't know how much I believe that number though. But
Mark?
Hi, Henrik.
So
obviously your last ALMA slides were fantastic, no doubt about that. But I just wonder, could you, instead of the teaser, also help us a little bit with the interpretation? Because we know this environment is special, the line widths are broad.
Yep.
Do these data help you to say something about shocks? And a little bit interpretation would be appreciated.
Yes, okay. So I'm not sure how much detail. So we have a lot of potential answers, things that we're working on writing up. A lot of our understanding is motivated by the simulations that Diederik and Jim have been running. So this is where they take, this is kind of getting back to, where's Hans? Getting back to Hans's question. So what they, Hans there. So these simulations take a gas cloud at Sag C and basically whiz it past the galactic center. So by doing that, because we have an idea what goes in and what comes out, we can compare directly to this. So we can see, there are some things that we expect from that. For example, gas is going to be getting shredded, ripped off. And so can we see that maybe in these absorption filaments that are lying in front of you saw in HCO+. So these are subthermally excited filaments that might be getting ripped off as the cloud has whizzed past. We can also, by comparing to these simulations, we can look for, not in an exact sense, we're never going to be able to show an image to image and make a direct comparison, but in a statistical sense, we might be able to say, where do we expect to see the shocks in the cloud? What kind of velocity gradient do you expect to see at that point in its passage past the galactic center? So I would love to be able to give you something quantitative. I'm happy to, well, if Diederik and Jim feel it's in a place where they can do that, then we have predictions based on these simulations that seem to match with things like the velocity gradient and gas coming off. But that's our best interpretation.
Ralph?
Did that answer your question? I'm not sure it was.
It's a start.
Okay, sorry. We can chat over a beer.
I'm wondering, in these beautiful ALMA data that you have, do you have the oxygen 1 line?
No, that would be fantastic if we did.
Because the models that Paul Clark and Simon Glover are producing with the chemistry and the full-fledged cosmic ray and UV radiation, they predict a 1 line to be very prominent and very bright.
Yes.
And this could be a way to distinguish between the UV and the cosmic ray flux.
Yes,
strength.
so that's one thing I didn't mention at all, is the fact that there's this weird thing in the gas and galactic center where the dust appears to be at 20 Kelvin and the gas is at 60 or 70. So this is either, if you do some modeling of this, is either shock heating or cosmic ray heating. And this O1 line turns out to be a really good way of distinguishing between those. This is something I've been doing with also working. I know you guys are doing it. I've been chatting with Mark Krumholtz about this as well. So that, yeah, it would be great, but I think Sophia's the only thing. Maybe Hans again, he's chatting. I think there's an instrument on Sophia that will be able to do that at high resolution. And that I definitely, as soon as that becomes available, I think that's a very interesting project.
Okay, thanks.
All right, great. Let's thank our speakers for a great session.